Hello guys, welcome to day number 9. Today we're gonna solve this problem and I hope you have tried to solve this at least, but if not then also nothing to worry because I'll give you a detailed explanation how we're gonna solve this. So if you have gone through this problem earlier, then you might have seen this one. They are saying something like do you need to use this features of Verilog. First of all, the question is that why should we use it, right? Till 8 days we have done codings in the Verilog, but we haven't seen it or we haven't used it. So what's the special things here that we need to have some new features of Verilog? So we will explain those things today, and you can say you are getting more introduction to Verilog features or the exact way how we write Verilog code. So Verilog have two special commands, and those are your initial. So as name suggests, you can think of something related to initializing your variables, data types, value, or something like that. We will see more around initial when we require it, but today for sure we're gonna use this always block. And always block, you can consider it as an infinite loop if you gonna compare it with the conventional coding. And in hardware, generally what is happening, things are going on in an infinite loop. Something is going on in infinite loop till the time you power off the hardware. So that's why always it's a very much important thing in Verilog, so that it can emulate the functionality of a hardware. So designing this shift register using D flip-flop and connecting them in a chain is easy for us because in our previous problem we have done it. The special thing is with this multiplexer. So first of all, we'll try to design a multiplexer, design a 4:1 multiplexer. Now, if you have remember the gate level view of your multiplexer, let me bring it up here. Then this is a gate level view of 4:1 multiplexer. And for sure, you can write your Verilog code in the gate level. And we have already seen few examples of how to write it. For example, here we are using a AND gate. So probably we will use the AND gate which is already defined in our Verilog, and here the first AND is a module. It's already defined in Verilog. We don't need to define it again. And the first port will be output. So for example, if this is your it is your output and its name is for example C. So you'll write here C, and then this 3 input. So you'll write this 3 input here and done. Likewise, we can generate S1, S1 not, S0, S0 not, and we can do this thing in gate level Verilog coding. But as I said, gate level is not so simple. For multiplexer, for sure it will be simple, but any time when your circuit will have thousands of gate, writing your Verilog code in gate level is never a wise decision. So that's where we do the behavioral description Verilog coding, where we just tell our Verilog simulator that hey, we need to achieve this thing, this is our logic or this is our algorithm, and you help us to synthesize it in the gate level and then further to the transistor level. So that is not our work. Luckily, synthesis tools are intelligent enough to synthesize the whole circuit from the algorithm which we have written in Verilog in behavioral description language. So what we'll try here in our example, we will try to build this multiplexer in behavioral domain. In gate level, for sure you can try sometime. It's a very insight, it'll give you more insight to learn your digital electronics. But for our task today, we will go for a behavioral description. So now to write your multiplexer in behavioral domain, you have 2-3 different way designing writing a multiplexer. One could be using a if-else conditions, or you can use a case condition, and I guess case is more readable. So as a beginner, it's better to start with a case statement, right? So we will start with a case statement, and just to refresh your memory how case work. Here what we write, we just write a case here and we give some expression, for example x, right? And then we give some condition related to the value of x. So we say hey, if x is equal to 1, then do this one. If it is 2, then do this work. If it is 3, then do this work, and so forth, right? And the same thing gonna happen here because you have your multiplexer here, right? And your multiplexer is driven by 4 input, and you want to select one of them and get it into the output. And who is controlling this thing? It is controlled by your select line, and your select line is of 2 bits. I have explained in last class why it is 2 bits. So I will write a case statement, and here let me remove okay, let me write it again. So in case statement, I will give this select line here as my controller, and then I'll say if our select line is 0 0, then pass the input 1. If it is 0 1, so I hope you are getting the things. So this is the logic we will implement in the Verilog syntax, following the Verilog syntax, and synthesizer will do the work to synthesize this thing to the gate level. So it's easy for us, right? So let's do it. And before I start, please give your attendance by liking this video. So there they have defined the top module. What is your top module? This black box you can see, right? Black border box. This is your top module. Inside top module, you need to instantiate the D flip-flop 3 times, and then you need to have this and for this multiplexer we gonna need to write this case statement. So what I'll write case, and inside case I'll give my the control structure. The control structure is select here, but select is of 2 bit, right? And it is already defined here. So I am giving the whole select here, and then I'll go inside and I will write if my select is 0 0, then what we should do? We should do, see, just go to your diagram here. If it is 0 0 here, your select line is 0 0, then you need to select the 0 input, right? This one, and this one will get connected to the Q or to the output of your top module. So my Q will be equal to this one, this fellow D, which we getting from the input of your top module. So I'll directly write Q equal to D and then semicolon. Now if it is 0 1, then the output of first D flip-flop will go as Q. This will get connected to the Q, the output. Now this D flip-flop, this 3D flip-flop, we haven't instantiated them, so therefore we don't have any unique name for them because all of them have Q Q Q. So first we need to instantiate them. So let me take it and let me quickly instantiate it. In our last episode we have already done it, so I have written here, but for this last one I got confused. You might also get confused. So, and yeah, if you are a little bit confused about this thing, like first 2 lines and how I'm writing, then previous class episode you need to see again. Okay, but here this Q should not be following as our previous class. Here it will be a little different thing. So to eliminate this confusion, let me do one thing. Let me write all the net name here first, right? That we need to do here first. So here what we are doing, we are giving this one as our D1 out, this as D2 out, and then these 4 lines are there, right? So this is, we know this would be D2 out, this will be D1 out, this is directly coming from this D, right? So its name is D, and this would be the select line. But for this, so for now let us give it as D3 out, right? So then confusion will be clean and clear. So this thing need to come here. So after coming here, we need to write here D3 out. Also one thing we need to do, we need to define this D1 out, D2 out, and all D3 out. So let us do those things. That's done. Now if we'll come back to our case statement or the multiplexer design. So in multiplexer, if it is 0 1, your select line is 0 1, then I need to select this one, this fellow, and it is coming from this one, and this is, if we go here, it is your D1 out. So I will directly write here. And likewise, one wrong thing I am doing, I'll tell you. Let me finish it up. And if it is 1 0, I need to do 1 0 and then 1 1. Yeah. And if it is 1 1, then your Q equal to D3 out. Now the one issue I am doing, and that is I am defining here Q, but Q is not uniquely defined in our circuit, right? Q is used many times. You can see we have using here, then here also we have Q. What I am trying to achieve, and that is I want to touch this Q here, right? This Q should get assigned to this one, or this one. That's my aim. But here all q are not defined uniquely. But one thing you just need to remember, we are writing a code, a Verilog code for this top block, in top block. So in top block, if I anytime mention q, then it will directly get the access from this module definition. So in module definition, this q is a 8-bit and which is directly connected to, let me erase this, to this fellow, this one, this q. So that is perfect. So now the question is, yeah, if we want to get this q, then what's the procedure? Procedure is just what we need to do. We need to take the instance name. So this is your D2 instance of DF flip flop, and then dot and then q. So you will get the access of this q. So all done here. This is also done, but for case we need to close our case. To close our case statement, we need to write end case. So it is done. But now there is a very great questions, and the question is that, see how your Verilog code actually work and how your general coding actually works, C++. So in general purpose code, what's happened? Mostly, there are some exceptions, but mostly what happened? They will start running your code from line 1, and then they will go line 2, line 3, and then this, and then lastly they will come here. But in Verilog, this is not the way. As I said in our first class only, in Verilog you need to have some method by which you can concurrently run different blocks of code, because that's how hardware is working. If your hardware have 3 AND gate and you are giving input to this 3 AND gate, then this 3 AND gate will work at the same time, right? So that's what we need to achieve in our Verilog code. Otherwise we can't model a hardware here. Now here one issue is happening, and that is we have defined a case statement, or for us, let me write it here. You can use comment like this. We can write this is a multiplexer code. So it's a multiplexer for us, right? So now just go to your diagram and just tell me when this multiplexer should get activated, right? This multiplexer need to get activated to give us the result, and from our hardware sense we can say, hey, this multiplier need to be activated every time. Anytime something is changing in this signal, or this signal, or this signal, or this signal, or in the select line signal, then your multiplexer should work, right? It is not like, hey, if everything is happened, like I given some input here, it cross this one, this one, this one, and then only my multiplexer need to come into the picture. No, it is like it should be active always, every time. The point from where you have started, you have powered on your circuit, till the time it's powered off, your multiplexer need to be on. Same is true for these D flip flops also. And for the D flip flop, we already have a clock which is controlling it, right? Anytime we make any changes in the input and they got a clock enable, then my D flip flop transferring it to the Q bit. And same wise, this through this wire we are getting it to the second D, and we are getting it to the output Q. So for D flip flop it is happening, but for mask we don't know how it will be on for always. And that the exact requirement where we use the always block. Always block is like an infinite block. So if we put this multiplexer code inside a always block, that means this piece of code or piece of multiplexer will keep on working every time. But the question is that we can write always, but always also have some control. Like we can tell them, hey, anytime you get a positive clock, or anytime something is true, something is false, then only you run things inside the always block. But here in our case, see, anytime something is changing on select block signal, for example, it was 0 0, it changed to 0 1. So that time also we need to execute the multiplexer code, because then our input will change, right? Now your select clock is fixed to 0 0, it is not changing, but the output or the input to multiplexer got changed because some new clock arrived and we have given some new data. So that means this input also got changed. So your select is stationary, select is not changing, but still your multiplexer need to work. And if you think more deeply, then you will find out your multiplexer need to work anytime any signal is changing to be in safe side. So that's why actually we need to write like this, that always block, and inside we need to write all the signal name, because in always block inside these braces anything we write, those are called sensitivity list. So that means anytime anything are changing on those sensitivity list, your always inside the code of always block will start executing. And that's why they have given this star symbol, because star symbol will imply any wire is coming in this design, any signal is coming in this design, if they change, then please start running always block. So that's why here what we'll do, before this multiplexer code we will write here, and this is the syntax of it. So always at the rate, and then we provide the sensitivity list, and inside sensitivity we can write explicitly all the signal name, that is also perfect, but for shortcut we can just give the star. So now we have written always block, but how we will tell our simulator that hey, this part of the code is inside the always block? So that's why after you write always block, we have another keyword in Verilog, and that is begin. So this is the beginning of my always clock, and this is the end of my always block. It is same like curly braces we keep on using in our C++ coding. So if it is a C++ coding, then probably we don't have begin, and we will just write like this, so our simulator will understand. But for Verilog, this is the technique. You need to use begin and end keyword to let simulator know this is the perfect definition of your always block. So I hope everything is perfect, but I am also doubting some error is there. So let's see. I have submitted it. Yeah, we got some issue, and it is telling us net D1 out, which fan out to selector 0 cannot be assigned more than one value. Here something fishy is happening, I think. This should be D1 out, and this should be D2 out, and here this should be D2 out, right? Because see, your second flip-flop here, your D is coming from D1 out. This is your D1 out here. See, this is your D1 out. So your one input should be D1 out, and output should connect to D2 out. So I think that's one error, but this is a logical error we are doing. So D1, D2, and then D2, and then D3. Okay, let me submit and see. Now we got a result, but we got an incorrect result. And in the incorrect, they have given some hints also. So by following their hints, you can correct your result. They are saying output Q. Output Q means this the final output, this final output Q. So your output Q, what is happening? It's 171 mismatch, it is happening. And to debug it, you can also go to your warning messages. And from warning also, we can sometimes debug what is happening here. So in the warning, they are saying case item expression never matches to the, okay, let me see if some syntax error we are doing. This is the case statement. Okay, I got the issue. Can you guess what we are doing here? See, here you are giving that, hey, this is my select is my control of case. If select is equal to 0, 0, then do this and those things. But one issue we are doing, and that is we are not defining the 0, 0, 0, 1, 1, 0, 1, 1. Are they in decimal format? Are they in hexadecimal format? Because your Verilog support those, right? So we need to provide the format, and then so therefore we need to give this thing. And done, and let me submit. I hope we'll get a success message now, but it's good to see error also. Yeah, still we have 161 mismatch samples here. There is no warning, nothing. So how to know what we are doing here? Okay, let me see one thing. Okay, so after some time of debugging, I found out one silly mistake, very much silly mistakes, and that is, see, these wires, we are giving the definition of this wire, right? We are writing this is as D1 out, D2 out, D3 out. But these wires are not a single bits wire. They are multi-bit wire, or we can say they are a bus, or we can say they are a vector. But when we are defining them here, just see, we are not giving any dimensions here. And if we don't give any dimension, then vector will take a single bit. So what is happening? We are trying to give 8-bit output, but as our wire can't hold those, so we are just having those 1 bits, and we are just deleting, or we are just losing it out because our wire can't handle those. So let us fix it. So to fix it, we need to give the dimensions or the bits to your wires, and now these 3 wires are of 8-bit. Now submit, and I hope we'll get a success message this time for sure. And yeah, we got the success message, right? Now there is one question, and that is few of you might be having, and that is, how we are actually giving this stimuli to our circuit. In our circuit, for example, we have defined a selection here. Selection we know, and for sure we are not providing any value to selection. So what is happening? See, there is some other engineer who is writing a test bench for me, and in simple word, what does test bench is mean? Test bench is another module which will instantiate this top module, right? So they will instantiate this top module, and top module have how many ports? It have 4 port, 3 input and 1 output. So that output is your Q, and in a 3 input they have select line, they have D, and they have clock. Writing test bench, we need to provide many things, like we will have a monitor, like dollar, let me write it here, $ monitor. So it will monitor all the output, then we will initialize those values. But don't worry, in future classes we will also try to learn writing these test benches. But for us now, this test bench is already written. We are just designing the device under test DUT, but test bench is already there in the HDL bits environment, right? So now if you just write this same code in any other simulator, for example EDA Playground is there, then you write it in some installed software like GTK Wave or Model Sim or something like that, then it won't work, right? Because there we need to write test bench also, otherwise we won't be able to see the waveform. So that's why HDL bits is good, because in the initial days, now it's initial days for us, now we need to give concentration to learning the code, not writing those test bench and those things, because those are easy tasks. For example, if, and you can try out this one, like this task, you can just go to your EDA Playground, and in EDA Playground there are 2 windows actually. In one window you need to write your device under test, the module, and in the another window you need to write the test bench of it. So you can do one thing, just as a homework, you can just copy this whole, but again if you go in EDA Playground, you also need to define this MyDFF8 also, like you need to define everything there, right? How your D flip flop is coming out of a single flip flop, and then a single flip flop is again made out of NAND gate or NOR gate. So everything you need to define, otherwise EDA Playground won't work. It's little complex work, so for now you can ignore, but in future for sure we'll do. Yeah, this is your EDA Playground. See, here we have the test bench and here we have the design. So currently we are only doing the design part, test bench part we'll do in future, don't worry. So now is the time to give the answer for the last day question, and last day question we have this one. It's a very logical question, and you might get this kind of questions in your screening exam of your BLSI company. So here say, in this line what we are doing, you need to remember this one, right? It is your bitwise, I have explained already in our last classes. It is a bitwise operator and it's a logical operator, OR operator. So logical OR operator will work on the whole things. So your A is 101, which is not a non-zero, it's a positive number, right? Your B is again 100, which is not a non-zero, it's a positive number. So for OR logic, if you have 2 positive number, then the output will be of 1 bit, and that is 1, true. For OR to become false, both of these need to be a 0, like not positive number is wrong word here actually, but they are not non-zero number, right? Non-zero number. So if you have both as 0 number, then only your logical OR will result you as 0. So that's why for out 2, for sure this could be the answer or this could be the answer, right? Now for out 1, here out 1 you are doing bitwise OR. So for bitwise OR you just write magnitude of your variables. So here bitwise OR 1 and 0, what will the answer? 1 and 0 will get 1 for OR, 0 0 will give 0, 1 1 will give 1. So the answer would be. So now the question for today, and that is this one, and also please write the explanation also. It will help you and your junior, your friends to get the correct answer, to know the concepts, and for sure we will explain the answer in our next video. So if you think I am adding value to your life, then please like this video, subscribe this channel if not, and you can share this video also. We will see in our next class. Until then, keep smiling and tata, bye bye.